Common potential of two capacitors charged to different potentials. Common potential of two capacitors charged to different potentials which are connected by a conducting wire. In the diagram, we have two capacitors, two spherical capacitors, and they are isolated. And these two capacitors have the capacitance as C1, C2, potentials V1, V2, and they are charged with the charge Q1 and Q2. And these two capacitors are connected by a connecting wire or conducting wire. These two capacitors are connected by a connecting wire or conducting wire, and final charge of the two capacitor after connecting them becomes Q1, Q2, and common potential is V. Final or common potential of the two capacitors become V and V. The common potential of the two capacitors, C1 and C2 is given by the common potential of the two capacitors C1 and C2 charged to different potentials V1 and V2 is given by charge to different potentials V1 V2 which are connected by a connecting wire or conducting wire is given by V equal C1 V1 plus C2 V2 divided by C1 plus C2. V equals C1 V1 plus C2 V2 divided by C1 plus C2. That is the common potential of the two capacitors C1 and C2 charged to different potentials which are connected by a conducting wire or connecting wire. In this case, the charge flows from the capacitor C1 at higher potential. The charge flows from the capacitor C1 at higher potential V1 to another capacitor C2 at lower potential. Another capacitor C2 at lower potential V2. In the diagram, V1 is greater than V2, that is potential of the capacitor C1 is greater than the potential of the capacitor C2. When the two capacitors are connected by a conducting wire, delta amount of charge will be shared from the capacitor C1 to C2. Delta Q be the amount of charge which will be shared through the conducting wire or connecting wire from the capacitor C1 to C2. Yet the charge flows from C1 to C2 through the conducting wire or connecting wire. Next, formula number 11. Loss of energy due to sharing of charges between two capacitors. Loss of energy due to sharing of charges between two capacitors connected by a conducting wire, or conducting wire. So here V1 and V2 are the different potentials of the two capacitors C1 C2, and these two capacitors are connected by a conducting wire. In this case, dq amount of charge will be shared from the capacitor C1 to C2. That means the charge will be shared from the capacitor at higher potential to the capacitor at lower potential. In this case, the two capacitors are connected by a connecting wire or conducting wire. It should be conducting wire in the diagram. Total initial energy before sharing of charges between the two capacitors is given by total initial energy before the sharing of charges between the two capacitors is given by Ui equal half C1 V1 square plus half C2 V2 square. Again, the total final energy or total energy of the two capacitors after sharing of charges due to connection after connecting the two capacitors by a conducting wire, or total energy of the two capacitors after sharing of charges is given by UF equal half C1 V square plus half C2 V square. UF equal, and now energy, initial energy of C1 was half C1 V1 square, and final initial energy of the capacitor C2 was half C2 V2 square, and final energy of the capacitor C1 becomes half C1 V square, and final energy of the capacitor C2 becomes half C2 V square. Now Ui is greater than UF. Therefore, delta U equal Ui minus UF, as Ui is greater than UF. Therefore, delta U equal half C1 C2 divided by C1 plus C2, half C1 C2 divided by C1 plus C2. Bracket closed. Under bracket V1 minus V2 whole square, that is square of difference in voltage. So it can be proved, and this is the expression of loss of energy. This is the energy expression of energy loss or loss of energy due to sharing of charges between the two capacitors. Energy loss on sharing of charges between the two capacitors when they are connected by a conducting wire. Delta U equal 1 by 2 C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. Now the loss of energy appears as the loss of energy appears in the form of sparking and heat produced in the conducting wire, or connecting wire. The loss of energy appears in the form of sparking and heat produced in the conducting wire or connecting wire. And here in total initial energy of the two capacitor was Ui, which is half C1 V1 square plus half C2 V2 square, and final energy becomes UF equal half C1 C2 bracket closed into V square. Here delta U will be the loss of energy, which is half C1 V1 square, half C1 C2 square divided by C1 plus C2, and delta U is a loss of energy which appears in this connecting wire as sparking and heat. The capacitance, number 12 formula, is the capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor with a dielectric slab. We can draw a diagram of parallel plate capacitor with a dielectric slab. That means number 12 formula, capacitance of a parallel plate capacitor with a dielectric slab, and this is the diagram of a parallel plate capacitor with a dielectric slab. So these are the two plates. And two plates of the parallel plate capacitor. First plate is charged with positive charge, and this is the induced negative charge on the inner face of the parallel plate capacitor, and this is the dielectric slab which is introduced in between the two plates. This is the dielectric slab of thickness T and dielectric constant K. Field intensity acting outside the dielectric slab is E0. That is the field intensity acting in vacuum. That means the medium between the two plates is vacuum, and field intensity acting in this vacuum is E0, and field intensity acting inside the dielectric slab is E. Dielectric constant is K, and epsilon is the permittivity of the dielectric slab, and epsilon 0 is the permittivity of vacuum outside the dielectric slab. We can denote the thickness. T is the thickness of the dielectric slab, and D is the distance between the two plates of the parallel plate capacitor. We can denote the potential difference between the two plates. V is the potential difference between the two plates. Capacitance of this parallel plate capacitor C equal Q by V, and potential difference between the two metallic plates of the parallel plate capacitor is given by V equal E dot T plus E0 dot D minus T. E is the field intensity acting inside the dielectric slab, and E0 is the field intensity acting outside the dielectric slab, that is field intensity acting in vacuum. Now E equal E0 by K, that is field intensity acting inside the dielectric slab, E equal E0 by K, and field intensity acting vacuum is E0 equals sigma by epsilon 0. Therefore, C equal epsilon 0 A divided by D minus T bracket open 1 minus 1 by K. C equal epsilon 0 A divided by D minus T bracket open 1 minus 1 by K. This is the capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor with a dielectric slab between the two plates of the capacitor, such that the thickness of the dielectric slab is less than the distance between the two plates. That means T is less than D. Small t equal thickness of the slab. Small d is the distance between the two plates of the parallel plate capacitor. D is the distance between the two plates of the parallel plate capacitor. Additional information here: C0 is the capacitance of a parallel plate capacitor with vacuum. The intermediate medium between the two plates of the parallel plate capacitor is vacuum. These are the positive charge and induced negative charge. C0 equal epsilon 0 A divided by small d. So this is the expression of capacitance of parallel plate capacitor with vacuum. C0 equal epsilon 0 A divided by D, that is the capacitance of a parallel plate capacitor with vacuum. Capacitance of a parallel plate capacitor with vacuum. D is the distance between the two plates. Epsilon 0 is the permittivity of vacuum. Now we can draw the diagram again. The parallel plate capacitor, these are the two plates. A dielectric slab is introduced in between the two plates. T is the thickness of this dielectric slab. D is the distance between the two plates of parallel plate capacitor. These are the positive charge and induced negative charge. K is the dielectric constant of the dielectric slab, and C is the capacitance. C equal epsilon 0 A divided by D minus T bracket open 1 minus 1 by K bracket closed. C equal epsilon 0 A divided by D minus T 1 in minus 1 by K. That is, this is the capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor with dielectric slab such that T less than equal D. T less than equal D. So here dielectric slab is introduced in vacuum between the two plates of parallel plate capacitor. Dielectric slab is introduced in between the two plates of parallel plate capacitor. Now C by C0 is equal to D divided by D minus T 1 minus 1 by K. That means C greater than C0, that is if a dielectric slab is introduced is introduced between the two plates of the parallel plate capacitor. Between the two plates of the parallel plate capacitor. Parallel plate capacitor. Capacitance increases. Capacitance increases. Capacitance increases. In the diagram, the capacitance with vacuum was C0, which was epsilon 0A divided by D. Now capacitance increases to C equal epsilon 0A divided by D minus T into 1 minus 1 by K. Number 14 formula or number 14 topic is capacitance of a parallel plate capacitor. Capacitance of a parallel plate capacitor with a metallic slab or with a conducting slab. With a conducting slab or that is metallic slab. Capacitance of a parallel plate capacitor with a metallic slab. In the diagram, positive charge and induced negative charge are denoted to the plate of parallel plate capacitor. To the plate of parallel plate capacitor. A metallic slab is introduced in between the two plates of parallel plate capacitor. K is the dielectric constant, epsilon 0 is the permittivity of the conducting slab, T is the thickness of this conducting slab, and epsilon 0 is the permittivity of vacuum outside the metallic slab. This is the metallic slab which is introduced in between the two plates of parallel plate capacitor, and dielectric constant and permittivity of metallic slab are K and epsilon. D is the distance between the two plates such that T is less than D. Thickness of the metallic slab is less than D. Field intensity acting inside the metallic slab is E, which is E0 by K, where K is the dielectric constant of the metallic slab. Field intensity acting outside the metallic slab is E0. E0 is the field intensity acting in vacuum, that is acting outside the metallic slab, and E0, that means E0 is the field intensity acting in vacuum. Q is the charge given to the plate, and V is the potential difference between the two plates of the parallel plate capacitor. In this case, capacitance C equal Q by V, charge by potential difference, and the potential difference between the two plates of the metallic slab is given by potential difference between the two plates of metallic slab of the capacitance or of the parallel plate capacitor is given by V equal E dot T, field intensity into thickness or distance, plus E0 D minus T, where E is the field intensity acting inside the metallic slab and E0 is the field intensity acting outside the metallic slab. Now E equal E0 by K, field intensity in vacuum divided by dielectric constant of metallic slab, that is E0 by K, which is equal to E. E is the field intensity acting inside the metallic slab. E equal E0 by K, which is the field intensity acting inside the metallic slab. Inside the metallic slab. E equal E0 by K. Now K is equal infinity. K is equal to infinity, which is the value of dielectric constant for metal or conducting slab. K equal infinity, which is the dielectric constant, for metallic slab or for metal. Therefore, E0, and again E0 equals sigma by epsilon 0. E0 equals sigma by epsilon 0, where sigma is the surface charge density of the plate of the parallel plate capacitor. That means E0 equals sigma by epsilon 0, which is the field intensity outside the metallic slab. That means field intensity acting in vacuum between the two plates of parallel plate capacitor. Therefore, C equal epsilon 0 A divided by D minus T. C equal epsilon 0 A divided by D minus T, which is the capacitance of a parallel plate capacitor, which is the capacitance of the parallel plate capacitor with a metallic slab or conducting slab such that T is less than D. Capacitance of a parallel plate capacitor with a metallic slab which is C equal epsilon 0 A divided by D minus T. Now dielectric constant K equal infinity for metal. Field intensity inside the metal is 0, that is E equals 0. Field intensity outside the metallic slab is E0 equals sigma by epsilon 0. Potential difference between the two ends of the metallic slab is V1 equal E dot T. Potential difference outside the metallic slab is V2, which is E0 dot D minus T. So now C equal epsilon 0 A divided by D minus T, which is the capacitance of parallel plate capacitor with a metallic slab such that T less than D. Change in capacitance, comma, potential, comma, charge and energy. Change in capacitance, potential, charge and energy of a capacitor due to introduction of a dielectric slab in between the two plates of the parallel plate capacitor, in between the plates of a parallel plate capacitor. We can draw a diagram of parallel plate capacitor with vacuum only. This is the parallel plate capacitor with positive charge and induced negative charge. Q is the charge given to the plate and D is the distance between the two plates, and intermediate medium between the two plates is vacuum. That's why permittivity of vacuum is epsilon 0. Capacitance of this parallel plate capacitor with vacuum is C0. C0 is the capacitance of this parallel plate capacitor with vacuum only. Now we can draw a parallel plate capacitor with a dielectric slab. This is the dielectric slab which is introduced in between the plates of the parallel plate capacitor. T is the thickness of this dielectric slab, and we can denote the distance between the two plates. K is the dielectric constant of the dielectric slab. We can epsilon 0 is the permittivity of vacuum. D is the distance between the two plates of the parallel plate capacitor. Initially, intermediate medium was vacuum. Now, a dielectric slab is introduced. This is the dielectric slab. When a dielectric slab is introduced, when a dielectric slab of dielectric constant K is introduced in between the plates of parallel plate capacitor, when a dielectric slab of dielectric constant K and thickness T is introduced in between the plates of a parallel plate capacitor with vacuum, in between the plates of a charged capacitor or charged parallel plate capacitor with a battery connected across the plates of the capacitor. In the diagram we can denote that a battery is connected to the parallel plate capacitor, and V is the terminal voltage of this battery, and again battery is connected to the parallel plate capacitor with a dielectric slab. This is the battery, and V is the terminal voltage. C is the capacitance of the parallel plate capacitor with dielectric slab. C is the capacitance of the parallel plate capacitor with the dielectric slab. That means when a dielectric slab is introduced in between the plates of parallel plate capacitor with the battery connected across the plates of capacitor, then the potential acting between the two plates, potential difference between the two plates, that is potential difference is V between the two plates, remains constant as battery is connected. As the battery is connected, that means battery is not disconnected from the capacitor. As the battery is connected to the capacitor, that means there is a connection between the battery and the capacitor. That's why potential difference between the two plates remains constant. V is the terminal voltage of the battery, and similarly V is the potential difference between the two plates of parallel plate capacitor. That's why potential difference remains constant, and Q prime is the final charge to the plate with dielectric slab, and here C greater than C0, Q prime greater than Q, U prime greater than U, but potential difference remains constant. V remains constant. Here capacitance increases, charge increases, and energy also increases, but potential difference V remains constant in this case. Initially, energy stored by the capacitor with vacuum only was U equal half C naught V square, and final energy stored by the capacitor, that means energy stored by the capacitor changes to U prime, which becomes half C V square. Initial energy was half C naught V square. Now final energy changes to half C V square. Number 2, the charge to the plate of the parallel plate capacitor, increases from Q to Q prime as the battery continues to supply charge to the plate of the capacitor. The charge increases from Q to Q prime as the battery continues to supply charge to the capacitor, Here delta Q be the amount of charge, which will be supplied to the capacitor continuously by the battery. And here potential difference remains constant, but the charge increases from Q to Q prime as the battery continues to supply charge to the capacitor. The capacitance of the parallel plate capacitor also increases from C0 to C. The capacitance increases, potential difference remains constant, charge increases. That's why capacitance increases from C naught equal epsilon 0 A divided by D to C equal epsilon 0 A divided by D minus T 1 minus 1 by K. Capacitance increases from C naught to C. Number 4, that is, what will be the change in energy? The energy stored by the capacitor also increases from u naught u equal half C naught V squared to u equal half C V square. As the capacitance of the parallel plate capacitor increases, that's why energy stored by the capacitor also increases from u to u prime. Now we can consider the diagram again. And in this case, initial energy stored by the capacitor was half C naught V square before introduction of dielectric slab, u equal 1 by 2 C naught V square. That was initial energy stored by the capacitor with vacuum only, that is before introduction of dielectric slab. U equal half C naught V square, which is the initial energy stored by the capacitor with vacuum before introduction of the dielectric slab. That means this is the initial energy stored by the capacitor with vacuum only. That means U equal half C naught V square. That was the initial energy stored by the capacitor before introduction of the dielectric slab in between the two plates. Dielectric slab in between the two plates. And energy increases to u prime, which is 1 by 2 half CV square. U prime becomes 1 by 2 half CV square. That is what the final energy stored by the capacitor. That is the final energy stored by the parallel plate capacitor with the dielectric slab. Final energy stored after the introduction of the dielectric slab. Final energy stored after introduction of the dielectric slab. Here capacitance increases from C naught to C. That's why energy increases from u to u prime. Energy also increases from u to u prime. Potential difference V remains constant, and as capacitance increases due to introduction of dielectric slab, that's why energy stored by the capacitor also increases.